let's start. We are done with conduction side. Okay, so as far as those that conduction side is concerned, I have completed, I think, 5 chapters. I just skipped the analytical solutions. Okay, we did not talk about the analytical solutions which were there for the steady state problems and the transient problems. The reason behind is obviously we have to cover convection and radiation and then the mass transfer as well. So we have to give due time to one portion. And the second thing is, this is a more practical approach. Learning the numerical technique, in most of the industrial problems you go for those things. And supplemented with your computer aided engineering subject or FEM or any other thing which is related to numerical methodology, it would be kind of more helpful. Okay, so but I think the mathematical stuff, the basics which we have covered, you can do it on your own, but that is not part of the exam anyways. Okay, so we move on to the convection side, and in that convection side, initially I would go through 3 things, right? And those 3 things are related to velocity, temperature and concentration. Initially, in this lecture, I try to give you an intro of these 3, and then we would keep that mass transfer aside, right? And we will talk about that in the end of this course, and then we would start covering velocity and thermal. Okay, but initially, just to set an analogy between all of these topics, I would simply give you an introduction about that. Okay, so let's talk about this convection thing. In the introduction, if you remember, we said there are 3 mechanisms: conduction, convection and radiation, and there are 2 which requires medium for heat transfer: conduction and convection. Okay, radiation does not need any kind of medium. As far as convection is concerned, you remember that you have to have bulk fluid motion. For convection, this is the main property. If there is no bulk fluid motion, even if you are talking about, let's say, a hot cup of tea, or let's say a hot tub of water, whatever it is, even if it is a fluid, if there is no bulk fluid motion, that heat transfer would be conduction. Okay, if there is some bulk fluid motion, let's say sea breeze flowing over sea surface, that air which is basically moving around this building, if you put this fan on, let's say, there would be heat transfer from all the objects within this room. Okay, so that kind of motion is there, and that is a bulk fluid motion. Now, what do you mean by bulk fluid motion? That a major chunk of fluid molecules should move with a considerable velocity. Okay, so that is basically bulk fluid motion. So convection is something that whenever fluid flows over some body, it can be solid, it can be liquid. 2 liquids can move over each other, just like air is flowing over the sea surface or a river surface. That fluid can move, let's say, around some building, air flowing around this building, right? So that is basically part of convection. And there are 2, we talked about the governing principle, I hope you remember. That was what? Newton's law of cooling. Okay, so that was the governing principle for convection. Generally it is considered, and that Newton's law says that Q dot, heat transfer rate, would be HAS Ts minus T infinity. So generally, in a broader sense, you can represent that heat transfer rate in convection through this relationship. Okay, and remember, those are kind of relationships which haven't been drawn from the fundamental principles. Now, what are the fundamental principles? Law of conservation of mass, law of conservation of momentum or energy. Those are the fundamental principles. Okay, these relationships, just like the Fourier law or Newton's law of cooling, they have been drawn from experiments. Remember that. Okay, so as far as the classification of convection is concerned, how many types of convection mechanisms are there? There are 2. Okay, I'm just giving you a recap of everything, and those are basically forced and natural. Okay, and in this case, forced case, you always have the bulk fluid motion from a source, and here in this figure, this fan is a source. Or if you blow, just try to blow, okay, and you try to blow to have a heat transfer from, let's say, some hot object. That is again kind of a forced mechanism of convection. But let's say if you do not install any kind of source for the fluid motion, which basically accelerates the fluid, fan basically accelerates the fluid. If there is no source as such, and you try to do everything, let's say, without any kind of force, for example, this is the hot plate and air is simply flowing over this. Now whenever air makes a contact with this hot object, it gains temperature and its density is affected by that temperature. You can say it loses its density, right? And it starts moving up. It starts moving up, okay? So that's how you see those strong winds coming up in different regions, okay? So this is basically, you can say, natural convection. This is an example of natural convection where you do not put any kind of source to accelerate the fluid motion. So as far as this convection is concerned, you generally quantify that convection mechanism through a convection coefficient, heat transfer coefficient, right? And that is H. And in that introduction, I told you that this H can only be measured experimentally. It is not a fluid property, it is a flow property. Remember that. H is not a fluid property. It is what? Flow property. Flow property means whatever is affecting the flow, it would affect H, right? And I just copied and pasted that paragraph which describes what kind of flow properties are there which can affect the value of H, okay? So convection heat transfer strongly depends on fluid properties, just like dynamic viscosity, thermal conductivity of the fluid. I am talking about thermal conductivity of the fluid, I am not talking about thermal conductivity of the solid, okay? So density, rho, and specific heat, which is Cp, right? So although you can say velocity is also dependent on H. For example, if you put the fan on, H would increase, simple as that. And if H is increased, you can say heat transfer rate is increased, right? So please remember this thing, that H is not a fluid property. H is a property of flow, right, in totality. Now whenever you talk about convection, obviously it is associated with fluid motion. So whenever you talk about fluid motion, there are three equations from your fluid dynamics course: continuity and Navier-Stokes. Those equations are there, remember that, to govern. Those are the mathematical models to model what? Flow motion, fluid motion, okay? But before that, before discussing those Navier-Stokes equation and let's say supplementing everything with the energy equation, I just describe this concept of velocity boundary layer, okay? And you remember what is that velocity boundary layer? That happens due to viscosity of the fluid, okay? We have talked about this thing in detail and I have shown you some experimental videos as well in that course. So what you can see is, if there is a not a hot object, it can be any object, any solid surface, and if the flow is coming onto it, there would be a velocity boundary layer just like this one, right? This one. It would be having that parabola kind of thing, and this is what this is represented as delta x. The thickness of the velocity boundary layer is basically what? Delta x. And what you can see is, just to give you a recap, on this surface fluid molecules will have what velocity? Zero velocity. And as you start going up, that fluid velocity starts increasing, okay? And at this point you can say that fluid velocity becomes equal to what? 0.99 of u infinity. You remember we took that definition in that course. So when the fluid velocity becomes 0.99 of u infinity, you say that it is the edge of that boundary layer, right? And the gap between that edge at any point on the plate, let's say on this section, this gap defines what? velocity boundary layer thickness at this section x. Okay, and as you go along the plate, that boundary layer grows, right? So what you can see is the more important point where I would be interested. Generally, as far as that convection coefficient, this convection related studies is concerned, we will be talking about two coefficients and different forms of these two coefficients. You can say that this is something known as friction coefficient. That convection study would be centered around this thing, and then there is convection heat transfer coefficient. Right now, just see, you see there is friction. If you look at this velocity layer, fluid layer, which is sticking to that solid, it would have zero velocity. There is a friction, and as you move up, that velocity increases. It means due to that friction, there is something which is known as shear stress. I hope you remember that. You remember that tau term? Okay, there would be a shear stress. Why? Because fluid layers, they try to stick with one another and they try to move over one another. Okay, and there is viscosity, and viscosity is something which provides resistance against anything which tries to change the shape of the fluid volume, you can say. Okay, so there is some quantity which is known as shear stress, and that is a measure of friction. Exactly. Yes, at the surface of the plate, friction would be kind of maximum, right? So just going point by point, you can say there are velocity gradients. And how do you define that shear stress? Okay, let me define that shear stress. You say that if shear stress is directly proportional to this thing, velocity gradient, partial u by partial y, u is what? This is x velocity. We are just talking about flow over a flat plate. So u is x velocity and y is something which is showing the vertical direction. Okay, so this is partial u by partial y, which represents a velocity gradient. You remember that velocity gradient? Okay, where you took this thing in your fluid mechanics course, right? I would not go into that detail because we have already discussed all of those things in great detail in the fluid mechanics course. So please keep your fluid mechanics notes with you or some book. Okay, I would recommend that. So tau is proportional to partial u by partial y. So partial u by partial y, this is the velocity gradient, right? If shear stress is directly proportional to partial u by partial y, what kind of fluid it would be? Newtonian fluid. Newtonian fluid, right? That fluid would be if this relationship between the shear stress and velocity gradient is linear, you would say you are dealing with a Newtonian fluid. If that relationship is non-linear, for example, what kind of non-linearity can be there? Shear stress tau can be proportional to, let's say, partial u by partial y whole square, for example. Then you can say it is a non-linear fluid. You understand that? So if I just convert this proportionality sign into equality sign, there would be a quantity mu, and you would write it as partial u by partial y, and this mu is what? Dynamic viscosity. By the way, there is something which is kinematic viscosity as well, right? So this is mu. We would use that term as well. So just see, velocity gradients and shear stress are large within the boundary layer. So within the boundary layer, you would see that velocity gradients are large. For example, if you go outside the boundary layer, let's say outside the boundary layer, I am just talking about some point over there, and there is some point over there. So it would have some velocity u2 and it would have some velocity u1. For example, if I ask you what is partial u by partial y over there, outside the boundary layer, it should be 0. It should be 0, isn't it? Why? Because outside the boundary layer everything is like u infinity. Okay, so there is no change in velocity as you move up outside the boundary layer, right? So you can say that velocity gradients and shear stress, velocity gradient and shear stress, they are stronger in boundary layer, within the boundary layer, right? Now, with increasing distance from the leading edge, the effects of viscosity penetrate further into the free stream. It means it grows. That velocity boundary layer grows. So as it grows, it penetrates into the free stream. Okay, just like this one. It starts from this point and it starts penetrating in the free stream region. So into the free stream, and the boundary layer grows. And as you move along the plate, that thickness starts increasing. Now, shear stress and friction coefficient depends on x. Why? Because this thing is related to delta. This is a function of x. This is a function of x. If this is just y direction and this is x direction, just see that this is the plate. I am just considering it a plate, this axis. And as you move along this plate, that thickness increases. Now see, what is the velocity over there? 0. What is velocity over there? U infinity. Now, what is velocity over there? The same velocities, isn't it? Now you see, at this point, velocity has to cover this lesser gap to reach to a value of, but here it has got a larger gap. You remember that discussion where we talked about how partial u by partial y varies along different sections, whether it increases or decreases. We will talk about that in detail as well. But I am just taking this thing into the discussion just for a recap, right? So you can say that shear stress and friction coefficient depends on x. Now due to this reason, shear stress would become a function of x. Why? Because partial u by partial y at all the stations, that is a function of x. Partial u by partial y. Okay, that is a function of x. As you move along the plate, at different sections you would find different values of partial u by partial y. Is that understood? Any problem? Okay, so shear stress at the wall. Shear stress at the wall is defined as mu partial u by partial y at y is equal to 0. Why? Because we start measuring y from the plate itself. So if I ask you what is the shear stress at the wall, and you have some function for partial u by partial y, so you need to calculate partial u by partial y at y is equal to 0 and then multiply it with mu. Okay, so you can say that at y is equal to 0 you would have wall shear stress. You would have a subscript w over there, and this is known as wall shear stress. Okay, and whenever you try to non-dimensionalize things, again as an engineer you always try to non-dimensionalize the things. You remember that discussion, that Buckingham Pi theorem, and right? So as engineers you would find that in most of the literature you try to talk in terms of non-dimensional things. Okay, so that shear stress, if you try to non-dimensionalize this shear stress by dynamic pressure, that is a quantity which is known as friction coefficient. That is a quantity which is known as friction coefficient. Okay, remember that. If you try to non-dimensionalize this wall shear stress, I repeat, this wall shear stress at y equals 0, the value of shear stress at y equals 0. If you try to non-dimensionalize this wall shear stress by the dynamic pressure, it is friction coefficient. Remember this thing. You can see this definition over there. Okay, so friction coefficient is one of the most important parameters in convection studies. Right? Any question about this thing? Sorry? Viscosity effect does not grow, you can say. Sorry? It penetrates. You are talking about that term? That penetrates? No, it means that here you would have the maximum friction, isn't it? At this point, fluid comes to know that it is sticking with the hot object, or let's say any solid object, right? So as you move up, so that feedback would be given to this layer, then this layer, then this layer, then this layer, and this pattern goes on. So this is what is meant by this penetration. It penetrates in the free stream region, right? It gives feedback to the upper layer, and then that gives the feedback to its upper layer, right? And that basically that is the reason for the development of this velocity boundary layer. If you have any other question. So that's it for today's lecture. I'm sorry we have no time now, so let's start the rest of the discussion in the next lecture.